7.1 symmetric matrix. I'm going to introduce symmetric matrix and some nice properties, theorems. This is really useful and really applicable to factorize a non-scalar matrix. We'll see in steps 7.4. Okay, what is a symmetric matrix? A symmetric a symmetric matrix is a matrix A such that A is equal to A transpose. Okay, so which means that A must be a square matrix. It can necessarily A must be a square matrix. So see example one. So let's say A is 1, 6, -2, -1, -2, 6, -1, and -1, -1, 5. There's a -1 in this one. So this is a 3 by 3 matrix, and then you can see that the all of non-diagonal entries are pairwise, right? -2, -2, -1, -1, -1, -1, right? So A must be symmetric, which means that A is equal to A transpose. Right? So let's find out. Let me just diagonalize matrix A. Okay, let me try. So I'm gonna find out eigenvalues, eigenvector first. Okay. So I want to try to decompose matrix A to PDP inverse. Okay. So to do that, I'm going to find out eigenvalues, eigenvectors. So first we need to get characteristic equation, right? Characteristic equation of A is 6 we do this A minus lambda I, and then we compute this one, right? That is equal to, let me just use, you can, let me use cofactor expansions, but let me skip the process. You're gonna get this minus, and then lambda minus 8, and then lambda minus 6, and then lambda minus 3. Please check this one if this is to see if this is right. But anyway, we got three eigenvalues. Lambda is equal to 8, right? And lambda equals 6, and lambda equals 3. Right. So for lambda, we substitute 8 into the lambda to figure out the corresponding eigenvector. Right? Okay. So then we solve A minus 8I, and then X is equal to 0 vector, right? We solve that homogeneous system, right? So to do that, then yeah, this one also, um, I believe you can do this one, right? So let me skip to find out to solve the homogeneous system. Then you'll get this one. Let me say V1. This is the eigenvector corresponding to lambda equals 8, minus 1, a -1, and 1 and 0. For lambda equals 6, then the eigenvector corresponding to 6 is a -1, -1, and 2. Okay. Then V equals 3, it's going to be 1, 1. Okay. So let's check to see if these are orthogonal, mutually orthogonal. Okay. So V1 dot V2 is equal to see -1 times -1, which is 1, and then 1 times -1 is -1, and then plus 0, right? So this is 0. And then V1 dot V3, so that should be must be 0. And then V2 dot V3 is equal to this one 0, 2, right? -2 plus 2 is 0. So as you can see that Vi, so which means that Vi dot Vj is equal to 0, right? Or I is not equal to 0. Okay. So which means that V1, V2, V3 are the orthogonal, right? And also V1, V2, V3 are linearly independent too. None of them are scalar multiple of other vectors. So you can say V1, V2, V3 is orthogonal basis of R3. So V1, V2, and V3 is on orthogonal basis for R3. Okay. All right, and then let me just let's divide. I mean, let's just rescale V1, V2, V3 so that these are orthonormal. I'm gonna find out the norm of each factors and divide them by their norm to make these are orthonormal. Okay. So let's say V1 over norm of V1 is equal to, what's the norm here? So norm of V1 is the discrete L2 norm, right? It's going to be square root of -1 square plus 1 square and plus 0, right? 0 square. So this is square root 2. So this is going to be -1 over square root 2, and then 1 over square root 2, and 0. And similarly, you can do that. Okay. You can just the scale down to the 1 by dividing the vector these orthogonal bases to the norm to make them to unit vector. So similarly, doing this here, norm is going to be square square root of 6, right? So we divide it by square root of 6. So we got -1 over square root of 6, -1 over square root of 6. And this is 2 over square root of 6. And V3 over V3. This is the way to make orthogonal basis to the orthonormal basis. This is 1 over square root of 3, right? 1 over square root of 3, 1 over square root of 3. Okay. All right. So now we construct the P. So let's say this is let me say this is U1. Okay. So let me put new name. This is U1. This is U2, and now this is U3. Then U1, you know, U1 and U2 and U3. And then matrix D, we construct the diagonal matrix using the eigenvalues. Okay, 8, 6, 3. Okay, so here 8 and 6 and 3. Okay, then PDP inverse. I mean, by the way, this is what orthogonal matrix, right? Each columns are orthonormals and they're linearly independent. This is orthogonal matrix. There exists inverse matrix, and the inverse matrix is P transpose, right? Then when you do this, P transpose and PDP P transpose, then you will get A. I think that's the purpose of this example. So for a given symmetric matrix, just find the eigenvalues and the corresponding eigenvectors, then construct the orthogonal matrix using eigenvectors, and then construct the diagonal matrix using eigenvalues. Okay, then PDP inverse will return the exactly same matrix, the A. Okay, so which means that if A if A is symmetric, okay. So here, then here. Okay. So if A is symmetric, then implies that what? The two eigenvectors from distinct different eigenspaces. For example, here. So any eigenvectors, pair of eigenvectors, this one or that, this one or this one, they are from the different eigenvalues, which means that whenever we pick the two eigenvectors from the distinct eigenspace, then they are orthogonal. That's one of the characteristic we can catch from that example. The next one is the I told you for A, if A is symmetric, then A can be decomposed a PDP transpose, which means that this one means that A is called the orthogonal diagonalizable. Not only this is diagonal, A is a diagonalizable, but matrix P in matrix P, its columns are orthonormals. I mean, P is orthogonal matrix. This is called the orthogonal diagonalizable. So here's a from that example, we can get two theorems. Theorem one is if A is symmetric, then two pair of the eigenvectors from distinct or different eigenspace. Okay, so eigenspace the distinct eigenspace means that these eigenvectors from different eigenvalues. Okay. So if A is symmetric, then pair of eigenvectors from distinct eigenspaces. That's theorem one. And theorem two. So A is symmetric. A is symmetric. A, let's say n by n is symmetric. Okay. So if and only if A is orthogonal and then diagonalizable. So I'm going to prove theorem one and two. Okay. So theorem proof of theorem one. So first one, let's say okay, pair of vectors from distinct eigenspaces are orthogonal. Sorry. So to show that two eigenvectors are orthogonal, we just pick the two eigenvectors arbitrarily and then do dot product, okay, and then show that the result is zero. That's simple. Okay. So let's say V1 and V2 be eigenvectors. Okay. Vectors from different. Definitely, we assume the A is symmetric. Okay, I didn't mention that, but we'll assume the A is symmetric, and then let's say V1, V2, the eigenvectors from different eigenspace. Okay, which means that what? Which means that A V1 is equal to lambda 1 V1, right? And A V2 is equal to lambda 2 V2, right? So we start from this lambda 1 times V1 dot product V2. Okay. So lambda 1 is a scalar. So if this one lambda 1 is eigenvalue, right? Because eigenvalue is non-zero. Okay. So if this one turns out to be zero, which means that V1 dot V2 equals zero, which means that V1, V2 are orthogonal. So proof is done. So do this, and then we want to get zero. That's the goal. So then V1 dot V2, first one, lambda 1 V1 is what? Lambda 1 V1 is A V1, right? So A V1. Before doing that, let me rewrite this one as a matrix form. So lambda 1 and then V1 transpose, right? 1 transpose and V dot V2. Okay, so we just so there's no dot product, the symbol of dot product. This is a matrix multiplication. This is equal to now when we can combine we can just put lambda 1 inside the parenthesis here because lambda 1 is a scalar. So transpose scalar is a scalar, right? V1 and transpose and V2. And now this is equal to lambda 1 V1 is equal to A V1, right? So A V1 transpose and V2. Oh. So now this is equal to taking transpose, we got V1 transpose, right? And the A transpose. And the A V2. Now we see that since A is a symmetry, A transpose is equal to A. So this is equal to V1 transpose and the A and V2. Now we use the parenthesis like this. The A V2 is equal to lambda to V2. So this is equal to V1 transpose and then lambda 2 and the V2. So now this is equal to lambda 2 and then V1 transpose V2, that's a dot product, right? V1 dot V2, right? So starting from this one, we got this. So now then move this one to the left-hand side to get 0 on the right-hand side. So we got lambda 1 minus lambda 2 and then V1 dot V2. This is equal to 0. I told you what lambda 1, lambda 2 are distinct, right? Because we got V1, V2 from the different eigenspaces, right? So it means that what? V1, V2, the dot product V1, V2 must be 0. Right? So proof is done. So V1, V2 must be orthogonal, right? So orthogonal, by the way, let me correct it. This is orthogonally diagonal, so sorry. Okay. So let me now let me prove theorem 2. Yes. The next one, I'm going to prove theorem 2. Which it says n by n matrix A is symmetric if and only if A is orthogonally diagonalizable. So I already prove it, and then should be I think I remember I posted the lecture video on YouTube. Let's see. Hold on a second. So, oh yeah, right there. You see that n by n matrix A is symmetric if and only if there exists a diagonal matrix D and the orthogonal matrix Q. Here I use the letter Q instead of P. Okay, but it doesn't matter. So, and the A is QDQ transpose, which means that A is orthogonally diagonalizable. Okay. So I'm gonna prove two way. Okay. So if A is symmetric, then yeah, A is orthogonally diagonalizable. And then if A is orthogonally diagonalizable, then A is symmetric. Okay. So here's a proof. Suppose that A is a QDQ transpose. So which means that we assume that A is orthogonally diagonalizable. Okay. And then that means the Q is orthogonal and then D is diagonal. Then A transpose, because well, we have to show that A is equal to A transpose. So just yeah, directly we're gonna calculate A transpose. So just computing A transpose like this, QD transpose and transpose. Then we got Q transpose transpose and D transpose Q transpose. So we got QD transpose, which is exactly the same as A. So A is symmetric. Because yeah, it's yeah. Then we assume that A is a symmetric. Okay. So and then for any symmetric matrix, we claim that A can be written in the form as A equals QDQ transpose. Okay. So case one. All right. So definitely we can find out eigenvalues, right? So what we can think about two cases. We have to think about two cases. The some eigenvalues are equal, or all eigenvalues are distinct, which means that multiplicity, probably multiplicity is just a one or greater than one. Okay, we think about two cases. Case one, lambda one is not equal to lambda two, which means that all eigenvalues are distinct, which means that multiplicity of each eigenvalue equals one. So then AV1 is equal to lambda 1 V1, and AV2 equals lambda 2 V2. Okay. The V1, V2 are n by 1 eigenvectors. Yep. Then since we assume the A is A transpose, right? So now then, lambda 1 minus lambda 2 times V1. Ooh, sorry. Oh, oh, sorry. Yeah, lambda 1 minus lambda 2 V1 transpose V2 is equal to this. I just distribute, the scalar, because lambda 1, lambda 2 scalar. The lambda 1 V1 transpose is A V1 transpose. Right? And the A V1, and then lambda 2 V2 is A V2, right? And just do transpose. Then we got V1 transpose, A transpose. But A transpose equal to A, so we got V1 transpose A V1, A V2. The right hand side, just copy it down. Okay, for here. Then you see V1 transpose A V2 minus V transpose. This is V1, okay? The V1. And then A V2 is equal to the 0, right? Because the quantity of this guy is equal to this, so 0. Okay, but lambda 1 is not equal to lambda 2, right? So we assume that lambda 1 and lambda 2 are distinct, right? Okay, which means that what? V1 transpose V2 must be 0. It means that what? V1, V2 are orthogonal eigenvectors, right? So, okay, once we figured out, okay, all of the eigenvectors are orthogonal, then by rescaling, okay, we can make them to of normal vectors by dividing its norm, right? So okay, then we can get the what? This one, orthogonal matrix Q, and then diagonal matrix is gonna be what? Just so you can get diagonal matrix using eigenvalues, right? All right. So now if lambda I is equal to lambda z, then we're gonna use Gram-Schmidt process to find the orthonormal vectors, right? Okay. So the proof is done. Okay. I didn't explain in detail, but this is the process the proof in this case is exactly the same as the Gram-Schmidt process. Okay. So we can build up the basis using by computing projection, right? So that's also a Gram-Schmidt process. All right, so back to here. Okay, so theorem 2, I just proved theorem 2. Let's see example 3. So example 3 is the case that some eigenvalues are equal. Okay, so this is the case that some eigenvalues are equal. What does that mean? Equal means that its multiplicity is greater than 1, right? So instead, the multiplicity of an eigenvalue is greater than 1. It's greater than 1. Okay. So let's see, example is 3. The matrix A is given by 3, -2, and 4, and -2, 6, 2, and 4, and 2, and 3. Okay. So we'll find out characteristic equation. Okay. So let's see, just step 1. Find characteristic equation. Okay. Then we got one, which means that we find the determinant of what? A minus lambda I, right? Yeah, right. Then we got this one. We got minus lambda minus 7 squared, and the lambda plus 2 is equal to 0. You see that? The lambda minus 7, this linear has a multiplicity 2, which is greater than 1. So we got only 2 eigenvalue, right? But to decompose A to PDP transpose, right? We need what, 3 eigenvectors, right? But they must be orthogonal and then also orthonormal basis, right? So how can you do that? Let's see, here's a solution. Step 1 and step 2. Find eigenvector. Okay. So for the lambda equals 7, okay. So V1 is going to be 1, 0, 1. Okay. I mean, the definitely to find the eigenvector, what we need to solve the system A minus lambda I, and then x is equal to 0, right? 0 vector right here. Then I'm sure that this matrix A minus lambda I has one free variable. Okay. Okay. So anyway, we got 2 eigenvectors, right? V1 and the V2. -1/2 and 1 and 0. But here's a question: can you get the more than 2 eigenvectors? Is it possible to get more than 2 eigenvectors? No, right? Keep in mind this: number of eigenvector cannot be exceed what? Multiplicity, because this is a 2, right? So we can only get at most 2 eigenvectors. So then V1 yeah, so V1 V2 must be linearly independent, because see, this is we cannot get this one as a linear multiple of this guy, scalar multiple of this guy, and then vice versa. So but are they orthogonal? I don't think so. Let me do this. V1 dot V2 is equal to, you see, -1/2 plus 0 plus 0. So -1/2. So this is not equal to 0. Oh, okay. V1, V2 are not orthogonal, but we need to get orthogonal, actually, orthonormal, right? Also, anyway, orthogonal basis. So how can this linear independence, okay, so we can say, okay, this, these two vectors span the R2, right? But we need to get kind of brand new basis which is orthogonal. How can I do that? How can I generate new basis which is orthogonal? Yeah, we can use a Gram-Schmidt. Let's say V1 is like this. Here's a V1. Okay. So let's say this is the space spanned by V1. Let's say W1. Okay. And then let's say this is a V2. V2. And then what we find out orthogonal projection of V2 onto the subspace W1. Let me use other color. This is better. This one. That's gonna be the projection of V2 onto the subspace W1. This is gonna be V2, dot product V2 and V1, right? Over norm of V1 square, right? That means what? This is equal to what? V1 dot V1, okay? And then times V1. And then now, well, we have to find a projection of V2 onto W1. Why? Because we want to get what? Basis vector other than V2 and orthogonal to V1. You see that V1, V2 are the basis. We can generate R2 using V1, V2, but they are not orthogonal. Okay, so we're gonna set this one we're gonna construct a new basis vector which are orthogonals. Okay, so the U1 we said just set the U1 as V1, and then by subtracting that projection, orthogonal projection from the V2, we can get what? The basis vector, which is orthogonal to U1. Let's say this is U2, okay? It's gonna be V2 minus the projection of V2 onto the space onto the space W1, subspace W1, okay? So this way, we can construct the orthogonal basis. That's the Gram-Schmidt process. What I did is to find out the orthogonal basis vector using Gram-Schmidt process. Okay. So do put the numbers in here and here. Okay. So combining everything, then you're gonna get that numbers end up with this number -1/2, and then no, -1/4, and a 1 and 1/4. Okay. All right. So now step 3 is to make what? Make the new orthogonal basis, the U1, U2 to orthonormal basis. Okay. So step 3. Okay, normal is called normalize. Normalize means that they rescale the vector to the vector whose the magnitude is 1. Okay. Oh, by the way, so right here, from there, so let me check it. If U1, U2 are really orthogonal, U1 dot U2 is gonna be, don't forget to check this, okay? U1 dot U2 gonna be what? So -1/4. Oh, this is positive, okay, not negative, sorry. This is positive 1/4. So -1/4 times 1 plus 0 times 1 plus 1 times positive 1/4, 0. Okay, so what? U1 and U2 is orthogonal basis. Orthogonal basis what? What's orthogonal basis what? Of the eigenspace, right? Eigenspace for what? Lambda equals 7. Okay, so yeah, right? Okay. Oh, I forgot to find out eigenvector corresponding to lambda equals -2. Sorry. So this one, give me a second. By the way, why this is why this is called the orthogonal basis? This is an orthogonal set, right? How come we can say this is a basis? Please look at the basis theorem. Okay, look at the just search the basis theorem. It should be in the textbook. I think chapter 4 or 5. Chapter 4, I think, yeah. Please the study basis theorem, okay? The step 3, before doing that, oops, sorry, we need to find out eigenvector corresponding to lambda equals 2, right? Okay. So here, now, so lambda equals 2, negative 2, right? Lambda equals negative 2, the V3 is equal to, if you're doing that, you're going to get negative 1 and negative 1/2 and 1. Okay, just skip the solution. Okay, so this is eigenvector corresponding to lambda equals negative 2. Okay, so and the eigenspace for lambda equals negative 2 is what? Just a line, right? So R1. Now move to step 3. Normalize U1, U2, and U3. Right? Let me say this is a U3, okay? To unify the the notation. So U3. Okay. So U1 gonna be U1 over norm over U1, right? It's gonna be one. What's the norm over U1? Norm over U1 gonna be square root 2, right? So this is 1 over square root 2, 0, and 1 over square root 2. Okay. And then U2 over norm over U2. It's gonna be what's the norm over U2? The square of this, square of this plus 1 plus square of this, and then taking square root, we got 18. Right? Square root 18. So we divide this one minus 1 over square root 18, and then 4 over square root 18, and then 1 over square root 18. Okay. The U3 over norm of U3. It's going to be this one. 1, 2, and then 1/4, right? So it should be I think 9, right? But before doing that, let me yeah, so it's gonna be normal V. Okay, this okay. V3 is gonna be square root of 1 plus 1/4 plus 1, right? So which is 3 over 2, right? 3/2. So we got negative 3/2, right? And then oh, give me a second. It should be yeah, so the norm is norm of V3 is 3 over 2. So we got this. Okay, I just normalize all three orthogonal bases, and then now we got orthonormal bases. Yeah. So P is gonna be what? U1, U2, and U3. And then D is gonna be what? So we just dearrange eigenvalues in order to match the order of the eigenvector. Okay. So it's gonna be 7, 7, and negative 2, and all other entry gonna be 0. Right. So yeah, if you have time, spare time, then just try to check if PDP transpose really return the A. Okay. Yeah. So from here, in this example, we can get many kind of highlighted property. So from here, U1, let me do this, U1 dot U3. Okay, U1 dot U3 is, here's a U1, right? U1 is a U1, right? U3 is what? This one. If you do this dot product of U1 and U3, it's going to be 0, right? And then v2 dot v3 is also 0. Is it right? So we can see that u1 dot u3 is 0, and u2 dot u3 is also 0. Okay, which means that what? Eigenspace, I mean, all of the vectors spanned by u1, u2 will be orthogonal to the vector spanned by u3, right? Which means the eigenspace, let me say this is w1 is spanned by u1, u2, which is what? Eigenspace of, right? This is the eigenspace for lambda equals 7. Let's say W2 is spanned, the subspace spanned by U3. This is eigenspace for lambda equals -2. It's not -2, right? Then these two eigenspaces are orthogonal. So W1 is orthogonal to W2. So if a matrix A is a symmetric, right? And then you find out eigenvector, eigenvalue, I mean orthonormal basis, then the eigenspace for each eigenvalues are orthogonal. Okay. What does that mean orthogonal means that any vector from W1 is orthogonal to any vector in W2. Okay, first one. The second one, the second observation from that example, I think I told that the dimension of eigenspace for each lambda is equal to what? Multiplicity. Okay, the multiplicity of that lambda. Okay, let me skip, the mentioning that one. Right. So what does that mean? Dimension of eyes. How can you catch this one from the example, the solution of that example? So I told you right here. I mean, I mentioned that the number of the eigenvalue will not be exceed what the multiplicity, right? Because we got two eigenvalues, eigenvectors, right? Because the multiplicity of the eigenvalue 7 is 2, right? Then that number of eigenvector cannot be exceeded, right? Which means that the number of bases will determine the dimension, right? So since we got two eigenvectors and these are well, linearly independent, and so these are linearly basis, right? So we got two basis vectors. So the eigenspace gonna be subspace in 2D. So the dimension of eigenspace for each lambda is the multiplicity. And third one, the A has what? N by N matrix, symmetric, okay, has N eigenvalues. Even even though some multiplicity of eigenvalue is greater than 1, so it has N eigenvalue counting multiplicity. Okay. So if here I'm talking about, this is a symmetry. So these are okay. These three observations are actually statements of a spectral theory. Okay, so I'm introduce spectrum theory or spectral theory. Okay, the what's a spectrum? This the spectrum is the set of eigenvalues. Okay, so the set of eigenvalues of matrix A. That is called the spectrum of A. This is called the spectrum. Spectral theorem for symmetric matrix is nothing but the summary of these observations. So the first one, we figured out all eigenvalues, I mean eigenvectors are the orthogonal, right? I mean eigenvectors from different eigenspaces are orthogonal, right? So eigenspaces are orthogonal, and then dimension of eigenspace for each lambda is the multiplicity. Okay. Then, which means that um the dimension of each eigenspace cannot be exceeded the multiplicity corresponding to the lambda. And then n by n matrix, symmetric matrix A has n eigenvalue counting multiplicity, and then theorem 1. So this is spectral theorem for symmetric matrices is nothing but the list the summary of the characteristic of the symmetric matrix. Now we're gonna see spectral decompositions. So using these the properties of the symmetric matrix, we can build up the decomposition technique. Okay. So suppose that A is can be decomposed as a P inverse. Okay. Definitely P is orthogonal matrix. Okay. So this is orthogonal matrix. I believe you can deconstruct the orthogonal matrix P. Right? Okay. So here P is the then orthonormal eigenvectors. Each columns of matrix P is orthonormal eigenvectors. So you say U1, U2 through the UN. Okay. So these are eigenvectors of matrix A. Okay. Corresponding lambda one through lambda n. Okay. Diagonal matrix D is just lambda one through the lambda n. So that doesn't mean that the multiplicity for each lambda for each eigenvalue is one. Okay. So if a certain eigenvalue has a multiplicity greater than one, then we repeat the writing multiple times. Okay. So then so it means that P inverse is equal to P transpose, right? Because P is a orthogonal matrix. So and now then PDP transpose is equal to the U1 through the UN, right? This here is interesting. This is equal to, and then times lambda 1 through the lambda n, right? 0. Here's a 0, right? And then P transpose is going to be what? U1 transpose, right? This one. Okay, U2 transpose. Through the UN transpose. Okay. Then this is equal to, let me just do multiplication in the first two matrices. Then we're gonna get lambda 1, right? Lambda 1 and U1, the lambda 2 U2, right? Through the lambda n UN. Okay. The times U1 transpose. This is a row vector. U2 transpose. The UN transpose. Now we're gonna use column row expansion. I mean, think about this. Then this is now using column rule expansion of the product, that is equal to this. Lambda 1, U1, the U2 transpose. This is a matrix multiplication, not dot product. Plus lambda 2, the U2, and then U1. Okay, sorry. U2 transpose plus through the lambda n, n and UN transpose. Really? That representation is called the spectral decomposition of A. So that is called spectral decomposition. Matrix A. Okay. So because matrix A is decomposed, I mean break up into the multi pieces determined by lambda 1. See, lambda 1 through the lambda 2 through the lambda n. You see that? A has been decomposed as a linear combination with weight lambda, which is eigenvalues. That's what this is called the spectral decomposition of A. Okay. And then what does U1, what does UI and then UI transpose look like? Aren't you curious about that? UI times UI transpose. So let's say UI, let me use a 1. Okay, let's say set I equals 1. Okay, U1 here. And then let's say this is a U1 is a n by 1 matrix. Then U1 transpose is going to be 1 by n matrix. So eventually we're going to get n by n matrix, right? Let's just figure it out. So right here. So U1, okay, so here, now let's say U1 is going to be, okay, U1, 1, and then U2, 1, UN, 1. Okay. Then U1 times U1 transpose is going to be U1, 1, U1, 1, and then U1, 1, and then what? U2, 1, right? Isn't it? Make sense? You didn't get it? So this is equal to what? U1, 1, U2, 1 through the UN, 1, right? Times what? U1, 1, U2, 1 through the UN, 1. Isn't it? And this is equal to U11 times U11, right? And then U11, U21 through the U11, UN1, right? The next one is what? U11, U21, oops. 21, U11, U21, U21, the U21, UN1, right? The last one is UN1, U11, UN1, U21, right? The UN1 times UN1. Is it? It's n by n matrix. Isn't it? So now, then this is equal to, I mean, by the way, that is called the projection matrix. Why? The projection matrix? Okay. For I equals 1. Okay. I think we use J, right? J equals 1. So in general, UJ and then UJ transpose. Here, U is the what? U is the the orthonormal, I mean, the normalized eigenvector of the symmetric matrix A, okay? So this is called the projection of matrix. Why is it called projection matrix? Because, here we go. That is equal to, just take a look at each columns. The first column, U11 is, commonly multiplied, right? So we can take that out, U11, which means that you can consider U11 as a scalar, and then the first term is a vector, U1, right? Similarly, second column, U21 is kind of scalar. So U21 times vector U D1, right? So similarly, we can say then that matrix can be written as U11 times U1 and the U21 times U1 through the UN1 times U1. It makes sense, right? So right here, you see that? That is a kind of scalar, right? Of the vector U. Is there any better way? Oh, yeah, this one. Okay. Okay. So U1 right here. U21 through the UN. Okay. All right. So now then, and you see that, by the way, U11 times U1, each column is what? Each column is just a scalar of U1. So what's the rank? What is the rank? Which means that what is the dimension of column space of A? This matrix, the matrix A will generate what? Only the vector, which is a scalar multiple of U1, right? So in this matrix, the rank of the uj in general, okay, in general, that is going to be what? 1. What is the rank? Dimension of column space of A, okay? The dimension of column space A. That makes sense, right? So this is rank 1, by the way. And then now, let me keep going. Why this is called the projection matrix? I just wondering. So that is equal to, by the way, let me do this. Uj transpose and X. Let me do this. Okay. So because I want to figure out why this is called the projection matrix, to figure out that, let me derive this. I'm going to derive this one. This is equal to, now there's going to be what? This is equal to U11, U1, U21, U1, through the UN1, U1, right? Because we figured out this one in here, right? And then X bar, that is equal to what? This is equal to what? First one, that is equal to, is equal to what? U1. Let me use 1, okay, instead of J, okay? It's easy to generalize, right? Because I just see the particular particular case, J equals 1. J equals 1, okay? Then U1 dot product to U1, isn't it? That matrix is equal to U1 or U1, right? So, oh, sorry, not this one. I'm sorry. Not it here. That is equal to X1, right? Is equal to, transpose is equal to this. X4 dot product to U1 and then U11, right? Okay. And then this is X or U1 and then U21. This is not product. Because of, yeah, I think let me do other way. I think you might be confused. So U1 transpose X bar is what? U1 bar U times, this is equal to what? U dot product, U1 dot product to UX, U1 and X and dot product, right? Here. So U1 here. Then you understood better, right? You better understood, right? Understand that. So this is equal to through the what? X dot U1 and UN1. Okay. That is equal to dot product of x and u1 is what? Just scalar. So we can take it out. Then we got this one times in u vector u, right? u1. So this is equal to x dot product of x and u1 over norm of u1 square in the u1. We can say that because u1 is orthonormal, right? So the norm of the orthonormal is 1. So that is 1, right? So it doesn't matter. We just divide this one by 1. That is 1, right? So what is this? This is a projection, right? Of what? X onto vector u1. Right. Okay. So we start from this one. We end up with this. What does that mean? This is what? Projection of x onto vector u1, right? In general, what? uj, the uj transpose and x is what? Projection of x onto uj. That's why that is called the projection matrix. So it means that which means that we could express the projection as a matrix form. Okay, so please see example 4 in the textbook.